16 cores on this machine. Run a CPU heavy Python script. Watch the core usage graph. Only one core lights up. The other 15 stay flat. Hey, I'm Kai and this is Fun with Learning Technology. That single lit core up there is not a bug in your laptop and you don't need a computer science degree to understand why it happens. By the end of this one, you will know exactly why threading alone won't speed up number crunching and what actually will. Inside the interpreter is a single lock. Only the thread holding it can run Python code. Every other thread waits its turn. Even with 16 cores free. But threads aren't pointless. The GIL is released the moment a thread is just waiting for a file, a network reply, a timer. So threads are great when your code spends most of its time waiting, not computing. Each fetch just sleeps for a second, standing in for a slow network call. Run the 4 rolls one after another and you pay for every wait in a row, about 4 seconds total. Lap each call in its own thread instead, and while one thread is sitting idle waiting on its reply, the others get a turn. Same 4 calls about 1 second because the waiting overlaps instead of stacking up. Same setup as before, but now each thread is grinding through 50 million additions instead of waiting on anything, before the number prints. What do you think happens to the total time with 4 threads running? Drop your guess in the comments. It comes back almost identical to running one thread alone, because there's never a wait for the GIL to hand off during just work, so one thread hogs it the whole time. Spin up separate processes instead of threads. Each process gets its own Python interpreter and its own GIL. Now, the cores really do run at the same time. Same count function, same 50 million additions, 4 of them. This time, a pool of 4 processes runs them, and each process has its own interpreter chewing through its own loop, with nobody waiting on a shared lock. Print the elapsed time and it actually drops, roughly 4 times faster, because the cores are finally doing real work at the same time. That speed up isn't free. Every process starts its own interpreter and its own memory, so spinning up 4 of them costs real memory, and they can't just reach into each other's variables the way threads can. For a quick script or light work, that overhead can cost more than it saves. Multiprocessing earns its keep on genuinely heavy, CPU-bound work, not as a default reflex. Managing raw threads or processes by hand means starting them, joining them, remembering to close pools. Easy to get wrong. The executor classes give one clean map call for both, and swapping thread pool executor for process pool executor really is a one-line change in this example. But that swap isn't always free. Process pool executor has to pickle every argument and return value to ship them to the other process. Code that works fine under threads. A lambda closure, an open file handle, a database connection passed into the function will blow up or silently misbehave the moment you swap in processes, because none of that pickles. So the choice isn't just threads. With just process wait, process pool executor has to pickle every argument and return. So, which do you reach for? Waiting on a network, a disk, a database, threading, crunching numbers on the CPU, multiprocessing, same 16 cores. Now you know how to actually use them.